Is it recording? There you are. Say good morning, class. All right, this is my first hour. Greeting you guys. There's Tish, all right. Tish Fan Club, right? Okay, so today we're starting on section 14.2, vapor pressure and boiling point. And we talked about the difference in boiling point and evaporation already. And which one happens at room temperature? Evaporation. Okay, and how do we know when something's boiling? Bubbles. Okay, those of you that are listening to this, you have to understand I'm standing in front of the room for you with this dorky headset on, and they're all staring at me like I'm crazy. Look at Sam's show right now, you'll see what I mean. Okay, all right, so this is for you. So, vaporization or evaporation. What is the difference between these? What phase is vaporization? Liquid to gas. Okay, how about evaporation? Liquid to gas, right? So when we were talking about evaporation and boiling, was it the same phase change? So this is the same thing. They are both going from a liquid to a gas. And when we start talking about vaporization, we're talking about if the pressure is involved and how quickly it's going to happen. So they both are, oh, I already had it right here, a conversion from a liquid to a gas. It requires energy to overcome strong intermolecular forces. So who can give me an example of an intermolecular force? What's one? Hydrogen bonding. Good. What's another one? Dipole, dipole. And what's the last one? London dispersion forces. Okay, so if you're that molecule in the solution, we have to overcome those forces in order to change that phase. Does that make sense? Okay. All right, so we have evaporation in an open container. Occurs only at the surface. We talked about this already. Occurs at a range of temperatures. Particles must have enough kinetic energy, energy of movement. They have to overcome those attractive forces. The air pressure speeds up when heated. So I already did this demonstration for you. But again, we have to remember that this only happens at the surface. Okay, so at the surface, these molecules have to have a certain amount of kinetic energy in order to change their phase from a liquid to a gas. So we've talked about this one. All right, so today we're going to talk more about vapor pressure. And it really is a cooling process. So Jackson, you're on the wrestling mat, working really hard. What is your body doing? Sweating. Okay. Why does our body sweat? Is it cools us down, right? And so on the surface of our skin, we're sweating, we're really warm, but when that sweat leaves us, can you kind of feel the coolness on your skin? Or if you go in a different environment, you sometimes get chilled? Okay, it's because our body is sweating. It's a cooling process to cool our body down so we don't overheat. And the particles with the highest kinetic energy are going to escape. Think about that. Does that make sense? The molecules that are moving the fastest are the ones that are going to escape, right? If they don't have enough energy, are they going to stay in the liquid phase? Yeah, okay. Average kinetic energy of remaining particles is lowered. All right, so if I go back to this, these particles here are moving really, really fast to get into this gaseous phase. Does it make sense that the kinetic energy down here is much less? Okay, all right, and that's what our body's doing when it sweats. So evaporation in a closed container, as particles vaporize, they collide with the walls and create a vapor pressure. And some particles return to the liquid and they condense. So this right here, oh, I keep on saying this right here, and they can't see me, and I keep pointing. I need to circle things so they know what I'm talking about. So this equation that I've now circled, it has an equilibrium expression. And you guys can see that it has a forward arrow and a reverse arrow. And so we've talked about when you have your water bottle, and it has some water that has been removed, and you have opened it. After you close it for a few days, would you see some water particles on top? Okay, that's at equilibrium. And there is a lot going on when you reach equilibrium. You have many particles going from liquid to gas, back and forth, back and forth, back and forth. And so a lot of times when you say the word equilibrium, you might be thinking, well, things are equal, it's done cooking, it's where it needs to be. But in this world, in a closed system, when you reach equilibrium, that's when the most action's going on inside of there. And so here you can see with this diagram, some are going to bounce out and bounce back down, out and out, up and out, whatever, whichever direction you're looking at, and they are going to reach equilibrium. So the rate of evaporation equals the rate of condensation. So in that water bottle, I know you can't see it, but there's a lot of action going on in the water that's inside. Okay? All right, so let's see. I think we want to... Okay, so I'm going to pause right here. I'm going to do a couple demos, you guys. Thank you. I know. Okay, we're back now. You missed some demonstrations. What did I do, you guys? Lit stuff on fire. Sorry that you were here. We asked someone to prom. That's right. I said yes. Oh, just kidding. Okay. All right. So vapor pressure increases with temperature. Hopefully from what you guys saw in the demos that if I were to increase the temperature of the acetone, would it even be more flammable? Okay, what do you think about the flash point of that acetone? High or low? Really low, meaning I don't need much of a flash point and it started on fire. You saw how it jumped, right? So the flash point is really low. Okay, so you guys can see the graph does the same thing. It shows you that as I increase the temperature here, that my vapor pressure is going up. Now, we saw between water and acetone that things can have different vapor pressures. And this graph right here is going to show you that. So we have the vapor pressure of, what is this? Methyl chloride, carbon tetrachloride, and water. And you can see water has the greatest vapor pressure, or the lowest vapor pressure. This is lowest. All right, so that means that it is not able to evaporate very quickly. And this one would have the highest vapor pressure because it's going to go from a liquid to a gas very easily. And we know water takes a long time to evaporate. This is just another demonstration of a manometer. We used to have these, but we had to get rid of them because it works best filled with mercury. But if you can think about the particles that I had down here, if I had water or acetone, they would go into a gas, and then they'd push through here. And if there's enough particles, then it's going to push this mercury up or down, and you'll be able to measure the difference in vapor pressure. Okay? We used to have that great demos of that, but we had to get rid of them. Okay, so you guys have in your notes, I have these questions right here. So these will be due by Tuesday. By the day of the test, we'll talk about any questions that you guys have on those on Monday. Okay, then the last section on 14.3, property of solids. I'm not going to talk about this going through right now. We're going to do a really short video on Boltzmann. And then tomorrow when you make the buckyballs, it will cover this section too. And then we'll finish that up on Monday. Okay. All right, so anybody have any questions? Okay, we have a greeting.
Hi, this is Mrs. Benson signing off. I hope all of you have a wonderful night, and I can't wait to see your smiling faces in school tomorrow. Have fun with the buckyballs. Don't let the bed bugs bite. Good night. Good night.